Okay, so in this video, we're going to implement that better solution for normal calculations that Lee talked about in the last video.
So I'm going to go ahead and stop Unity from running, hopefully. Come on, there we go. Let's jump back over to code. And for now, we're just going to implement everything inside of TerrainPatch. We'll go down to the bottom, create a new public static method, because this is going to be the same regardless. And it's going to return a vector3, which will be our normal, and we'll call this one calculate normal. And we need to pass in a vector3, and we're going to pass in, we're going to call it vertex. So our argument is going to be the vertex for which we want to calculate out our normal. We're going to need to know what our spacing is. So we can do it one of two ways. We can do it like before, where we go full spacing is the integer parsed from our config settings. And we can grab our setting, and then we can ask it for our patch vertex spacing. And it helps if I put that in quotes.
Mm-hmm.
You're just looking at the keyboard instead of the screen.
I understand.
So we could do it that way, but because this is the static method, we could also pass it in, or we can make our spacing for the entire class static. But in the future, we're going to have multiple sets of train patches. We're going to have a train patch that is going to be a higher density mesh that we're going to keep close to one of the cameras. And then we're going to have a separate camera that is going to be layered on for drawing a low density mesh that's going to be our terrain out in the distance, which will give us a much larger view distance. So for now, I'm just going to leave this method. And when we start doing the multiple terrain meshes, we're going to have to revisit how we keep track of what spacing is being used for which train patch system. So we'll need to create a couple more variables because we're going to have to go back and ask our train generator to give us the heights at different points. So we're going to need to look at our terrain demo. We created a train. I probably should fix the naming on that too at some point. So we're going to get our get smooth height. Now what we're looking for is going to be a passing in our x, which is going to be our vertex dot x, and our vertex dot z, and we need to add our spacing to it. So what we're doing is we're sampling the point directly above our current vertex that is one full space above us. So that will be our U sample. We need to do two more samples, or three more samples, my bad. We need our up sample. We're going to need one to the left. We're going to need one to the right, and one below us. So our up, left, right, and down samples. Our sample points for our left is going to be vertex minus one full space to the left. Vertex Z is going to be the same for our left and right because it is at the same height or the depth in Z. And our right is going to be one full space to our right. And down will be minus one full space. So if I go back into Photoshop real quick and I turn this off, turn on our grid again, what we're doing is, let's say our center point, or the point that we're sampling is right here. We want to get the point that's directly above us, directly below us, directly to the left and right. Now we could sample all 6 points and take the average, but our terrain system is fully capable of giving us the height right here. So instead of hitting the terrain generator, which is inherently slow because of all the calculations that it has to do, we want to minimize the number of times that we have to ask it for the height at any given position. So the less times we have to go get that information, the faster our algorithm and method will run. So once we've gotten those samples, we can calculate our normal. So var n for normal is going to equal a new vector 3, which will be our left sample minus our right sample in x. Our y component of our vector is going to be a full space. So if our spacing is 2, our y component will be 2. If it's 4, it'll be 4. This will help keep the lighting even. So what's kind of funny is you could technically take this and double it, and it will cause the lighting that you see on the train to almost double, because what happens is with the lighting calculations, you're almost telling it that that face is facing even straighter up than it was. So, but you want to keep it consistent. The reason we're using full space instead of, say, something like 1 is because our left and right and our up and down are being calculated based off of world units, which are being multiplied by our horizontal scale. So we want to make sure that our vertical scale, our what did I call it actually? Just make sure. Our max height. So everything, our y, our sample points in height, or our y, is being multiplied by max height. And because we're using our spacing in relation with max height, we want to make sure that all of our computed values are using the same relative scales. Otherwise, we might not get very accurate looking results, which is why we're going to use full space for our y. Now, we need to make sure that our normal is a unit vector, so we have to normalize it. So we're going to return n.normalized. This will return our normalized vector. So this is everything that we need to do to calculate a normal, but we have to calculate it for all of our vertices. So we'll create another method. This one's going to be a instantiated method. So public void calculate. I'm going to call this calculate values because we're going to use this to also calculate our tangents later on. We're just going to lay down the groundwork for now. So we need to set up for our normal. So var normals is going to equal a new vector 3 array of size mesh dot vertex count. So we want to create a new array of vector 3s. And that'll help if I type in vector 3. And we want it to be a vector, not vector 3s. But we want it to be the same size as the number of vertices that we have in our vertice list. Then we want to iterate through that list. So we'll use a for loop that is going to iterate through our mesh dot vertex count. And then what we're going to do is get out our vertex information. So create another variable called vertex to hold that. We're going to look at our mesh vertices array, get element at index I. We need to take that vertex, which is a vector 3, but it's relative to local space. So it's going to return something from 0 out to whatever our spacing and number of vertices per patch work out to be. So we're going to have to add our position to that. That will give us our vertex position in world space as opposed to local to or local to our patch. We're going to then take our normals array, get element at I, and assign it the value that we get back from our calculates normal method. Into that, we're going to have to pass in the vertex to calculate the normal for. The last thing that we have to do is we have to reassign our normals. Pause it.
You got somebody there. Hang on one
Yep.
second. We'll pause this. And we're resumed, Lee. I guess it was a false alarm.
Yeah, the dog just likes to bark. So, all right. So where we left off is we need to assign our array of normals that we just calculated to our mesh normals array. So we'll go mesh.normals equals normals. So that will assign all of our normals into it. But that's not going to do anything for us unless we call it. So we have to go up into update mesh. And actually, we can have some fun with it too. So it's like going, why do you need to calculate normals? Well, let's go ahead and comment out mesh.recalculate normals. And let's go ahead and run and see what happens. So
Awesome.
yeah, we end up not getting anything.
That's just fantastic.
So yeah, no normals to calculate lighting information. We also got an error too. So I want to see where that went to. So, oh yeah, well, if you don't calculate normals, you can't draw lines to them. So that makes sense. But basically, the normals are how you calculate lighting. That's where they are really important. So without normals, you don't get lighting information. So then the next question is, what do we need tangents for? Tangents are how we can calculate some of the more advanced functions of lighting, things like bump mapping and parallax.
But
we'll cover that.
Okay.
Yeah, I'm not going to dive into how we calculate or why. I'm just saying that because if we've got normals and normals give us lighting, then why do we need tangents?
I gotcha.
So, but instead of using the recalculate normals now, we're going to call calculate values. We don't have to pass anything in. So if we go ahead and run now, go ahead and clear that, close this out, run. Now this one will run a little bit slower than it did before, but not too bad. But that's because we've got something fairly small.
Right.
Now, a couple of things to notice. We get nice, smooth, even lighting all the way across the surface.
Mm-hmm.
There's no more seams. If you look at our little line widgets, we don't get the multiples along edges or the quad normals in corners anymore. So we're now using our terrain generator and using the basically slope calculation is all we're doing. We're calculating our left and right slope and our up and down slope and using that to generate our normals.
Right.
It's inherently a very fast, simple way of calculating good, even normal mapping. It's not the most accurate way because you're talking we're using two calculations to simplify or to interpolate what we could get with six different normals. So if this was a very complex shape, our lighting isn't going to be nearly as accurate as it could be. But we do have the advantage that we always know that based on our grid, we're always going to have vertices that are exactly one space apart. And we don't want super crazy differences in height inside of a single area of our terrain because then we'll have problems navigating it. So by knowing that we have this even spacing of our grid and that everything is going to be fairly smooth from vertice to vertice, we can get very convincing normal information by doing this method. Now, what I was saying that it's inherently fast, but this method is currently slower than what we can get inside of Unity, is because every time we're asking for those 4 points, we have to hit the train generator algorithm. And the train generator algorithm is going through and doing all the samples of all those different noise maps and our base map. And it has to do all the blending between it and the calculation to give us our final height. And then, it's got smoothing on top of all that. So each one of those points is fairly intensive to ask or to calculate, which is why this is running slower. Now, in the future, one of the things we're going to be implementing is going to be a vertex caching system, which is basically going to cache our vertices. And the very first time, or when you need information for a vertice, you're going to go to the cache and go, okay, does this vertice exist?
Vertex.
Sorry, vertex.
It's all good.
I get confused. Excuse me. But it'll go to the vertex cache and go, does this vertex exist? If it does, give me that information. If it doesn't, go calculate it, add it into the cache, and then keep it into the cache until it's gone so far outside of our area of interest and our time to live on it has expired. Then it will get purged from the cache.
Right.
So what we're going to do is we're going to optimize our system so we minimize the number of times that we have to go to the train generator. So with if you look at the typical playing of somebody in an MMO, they generally stick to a general area. Not many times do you go in the MMO and your entire day of playing is running from one end of the continent to the other and back and forth all day long. You usually find yourself in an area for a couple of hours at a time, and then you may go to another area and you stay at that area for a certain amount of time. So you tend to go from area to area, but you stay in those general areas for a period of time. So by doing a vertex cache, we're not going to be constantly generating the normals and the heights for each of these vertices over and over and over again.
Mm-hmm.
So we'll get a lot of the speed back that we're losing right now. We're just not going to worry about it now. This is more of a theory because we can do this right now before we have the sculpting tools to worry about, or the persistence, because part of the persistence system is going to get into interest management, which is going to have to get into the vertex cache. And then it gets into data storage and all kinds of fun, complex stuff that I didn't want to add to the complexity before we covered normals and tangents.
Right.
So,
okay.
But
so is that pretty much it then for normals?
Yeah. Well, there's kind of a nice little segue. Now that we've got this in, we can stop this. Let's go back and put our texture back on.
Mm-hmm.
Because now we've got it all fixed. We can go back and find our grass. Because I want to put the grass in and then demonstrate something else. Because we're calculating our lighting slightly different. We get an interesting thing that I like. We get more self-shadowing, or what looks like self-shadowing, where unities, especially when we start getting into complex shapes, let me do that too. When we start getting into complex terrains, and a lot of the terrain, I always found that Unity's lighting is too even. So it doesn't have enough, interest for my taste. And I prefer not to use dynamic shadows with all the penalties that are incurred from that.
Mm-hmm.
So if I jump this back up, let's go to 51, spacing of 2, still patch row count of that.
Okay.
And I have to turn off our draw normals.
Mm-hmm.
Because if I don't, Unity's not going to be too happy with you. It won't explode, but it's not going to run very fast. So if we go ahead and build out this one, I just want a larger area so we can look at the information that we get. I'm waiting for it to draw back in. Turn off gizmos too. So this does take longer to generate, especially the more vertices that you have in your patch, the slower this is going to get. So a lot of people who have been saying it takes too long to load new areas in, this just makes the problem worse. But you have to remember, these videos are R&D. This is more about technique than optimizing for real gameplay. So can you pan the camera around? It's not picking up for me. But if you look up in the areas where the detail is up in the hills, so we're getting darker areas than we would with the built-in. So if you get in close to, you won't see it too much, but you can see up in here along the edges where we get that nice dark areas in the detail. Whereas if I go ahead and stop this, and the jets are flying over today.
Yeah, I heard them.
So if we go ahead and turn back the normal calculation and we run it again, our meshes should load faster because we're not doing all of that information. But if you look up and where the detail is, it's not quite as dark.
Right.
We still have the depth in the areas where we had it before, but it's not quite as
no, not at all.
So I like the look that we get. It's also, if you start getting into shader technique, in essence, what we've done is we've applied slope lighting to our terrain. So we've used slope lighting to implement our normal map generation.
Gotcha. Very cool.
So, and then I want to demonstrate one other thing. Let's go ahead and hit pause, or not pause, stop it. There we go. All right, now back in the code, I want to use our new normal map calculation part. I'm going to drop our size down a bit. Let's go to config. Let's go down to 25. But I want to go back to TerrainPatch where I had mentioned we're using full space here. I want to demonstrate what happens if we double our spacing. Actually, to make it even more apparent, let's go by 4.
Okay.
So if we run it again, so what ends up happening is we brighten everything up. Those shadowed areas aren't quite so dark as they were before.
Right.
So everything brightens up. I might have chopped off too much information.
Yeah, I still think you can see it though.
Right. But we don't get that nice dark edge that we get. And so we're getting closer to what we get from Unity.
Right.
So it's almost like adding ambient light to our terrain without adding ambient light.
There we
So
go.
it's just a little trick that you can do. And then conversely, we can do the same thing. This will be the last one. If I can stop it. If we go and we divide, let's divide by 4. we darken everything up. We don't, it's not, the cool thing with this technique is it's not like ambient where everything blows out or everything darkens. We're darkening the shadows or lightening and darkening the shadow side of stuff.
Mm-hmm.
So we can, it's almost like giving us a little bit of shadowing for free. No performance hit for doing this, other than the fact of the calculation time for our normals.
Which we have to do anyways.
Yep.
Awesome. Okay, well then with that, that is going to wrap up our normal solution, and I guess we'll be moving into tangents next.
Tangents.
Yep. Awesome. Thanks a lot, everyone.